A functional dependency, FD, is a rule that says if you know the value of some attribute, you can always figure out the value of another attribute. In mathematics, we write it as x determines y, where x and y are sets of attributes. The meaning is, for any two rows called tuples in a table, if the x values are the same, then the y values must also be the same. Example, in a class list, the attribute student ID determines student name. We write student ID determines student name because every student has exactly one name for a given ID. The notation works for single attributes, A determines B, or for groups, A and C determines D. Explanation: functional dependencies can be sorted into several types. Trivial functional dependency: y is already part of x, like A and B determines A, it never gives new information. Non-trivial functional dependency: y is not inside x, for example student ID determines student name. Fully non-trivial functional dependency: no attribute of y is in x. The previous example is also fully non-trivial. Partial functional dependency: when a composite key x equals A and B determines y, but a proper subset of x, say A, already determines y. Example: in a table where country and city determines country code, if country determines country code already holds, the original functional dependency is partial. Transitive functional dependency: if x determines y and y determines z, then x determines z is called transitive. Think of a family tree. Knowing a parent x tells you the child y, knowing the child tells you the grandchild z. Therefore, the parent also tells you the grandchild z. These classifications help us see where redundancy or unnecessary data lives in a table. Armstrong's axioms are three simple rules that let us derive all possible functional dependencies from a given set. They are: reflexivity: if y is a subset of x, then x determines y, because a set always determines its own parts. Augmentation: if x determines y, then xz determines yz for any z. Adding the same extra information to both sides keeps the relationship true. Transitivity: if x determines y and y determines z, then x determines z. From these three we can prove other useful rules. Union: from x determines y and x determines z, we get x determines yz. Decomposition: from x determines yz we get x determines y and x determines z. Pseudotransitivity: from x determines y and yz determines w, we get xz determines w. These rules are like Lego bricks. Start with a few basic blocks, the axioms, and you can build any larger structure, all implied functional dependencies. The axioms are both sound, they never create a false functional dependency, and complete, they can create every true functional dependency. The closure of an attribute set x, written x plus, is the set of all attributes that x can determine using the given functional dependencies. To compute x plus, we repeatedly apply Armstrong's rules until nothing new appears. Step 1. Start with x plus equals x. Step 2. Look for any functional dependency y determines z, where y is a subset of x plus. If found, add z to x plus. Step 3. Repeat step 2 until x plus stops growing. Algorithmically, this is a simple loop and runs in big O of the size of f times the size of u, where the size of f is the number of functional dependencies and the size of u is the number of attributes. Example: suppose we have f equals the set containing A determines b, b determines c, and a d determines e. To find the set containing A plus, start with the set containing A. A determines b, adds b, resulting in the set containing A and b. B determines c, add c, resulting in the set containing A, B, and c. No more rules apply, so the closure of A, that is A plus, equals the set containing A, B, and c. Closure is essential for testing keys. A set X is a key if and only if X plus contains all attributes. A minimal canonical cover is a tidy version of a set of functional dependencies that has the same power but no extra fluff. To obtain it, we... Step 1. Split right-hand side. Make every functional dependency have a single attribute on the right side. A implies BC becomes A implies B and A implies C. Step 2. Remove extraneous attributes from the left side. For each functional dependency X implies Y, test each attribute A in X. If X minus a closure still contains Y, then it is extraneous and can be dropped. Step 3. Delete redundant functional dependencies. For each functional dependency, temporarily remove it and see if the remaining set still implies it using closure. If yes, discard it. The result is the smallest possible list of functional dependencies that behaves exactly like the original. It is useful because algorithms for schema decomposition work faster on minimal covers, and because it makes the designer's intent clear. Example, from a B implies C and A implies C, we see A implies C already covers the first functional dependency. Since a B implies C is implied by A implies C, after reduction we keep only A implies C. When we break a big table into smaller ones, we want two properties. Lossless join after splitting, and then joining the pieces back using natural join. We should get exactly the original rows, no extra or missing rows. The formal test for a decomposition of R into R1 and R2, the join is lossless. If and only if R1 intersect R2 determines R1, or R1 intersect R2 determines R2 holds in the functional dependency set. Think of a puzzle. The overlapping piece must be enough to lock the two halves together uniquely. Dependency preserving every original functional dependency should be enforceable without having to recombine the tables. This means the union of the functional dependency sets projected onto each subrelation must be equivalent, or at least imply the original functional dependency set. If a functional dependency is lost, the database would need costly joins just to check it. Often we aim for both, but sometimes a trade-off is needed. For example, BCNF decomposition may lose some dependencies requiring additional checks. Functional dependencies are the compass for spotting normal forms. 1NF, each cell holds a single atomic value. FDS don't matter here. 2NF, the table must be in 1NF and every non-key attribute must be fully dependent on the whole primary key. Partial dependencies, where a part of a composite key determines a non-key attribute, break 2NF. 3NF, in addition to 2NF, there must be no transitive dependency of a non-key attribute on the key. Formally, for every FDX determines Y, either X is a superkey or each attribute in Y minus X is a prime attribute, part of some candidate key. BCNF, stronger than 3NF, for every FDX determines Y, X must be a superkey. No exceptions are allowed. Using the FD list, we can test each rule by computing closures and checking the conditions above. For example, if we have student ID and course ID determines grade and student ID determines student name, the first FD is okay. But the second creates a partial dependency. Student ID is only part of the composite key, so the table is not in 2NF. Decomposing based on these violations, using the minimal cover, moves the schema upward toward higher normal forms. In real-world design, FDS guide us to store data efficiently and answer questions fast. Design phase. Talk to users, write down facts like a zip code tells a city. Turn each fact into an FD and build a minimal cover. Then decompose the big relation step by step, always checking lossless join and dependency preserving conditions. The result is a set of smaller tables that avoid redundancy and update anomalies. Query optimization. The query planner uses FDS to prune unnecessary joins. If it knows A determines B and a query asks for rows where B equals 5, the planner can first filter on A since each A gives a unique B which may use an index and avoid scanning the whole table. Index selection. An FD tells us which attribute uniquely identifies another, so we often create an index on the determinant left side to speed up lookups. Data validation. Constraints derived from FDS, for example unique on student ID, guarantee data quality automatically. Overall, functional dependencies are like the rule book of a game. Following them makes the database play smoothly and win the performance game. Explanation. Discovering FDS from an existing dataset is a data mining task. TANE, which stands for Tree-Based Algorithm for NRY Exploration, works like this. Level-wise search. Start with all single attributes, compute their equivalence classes, rows that share the same value. For each pair of attributes, check whether the partition of X is a refinement of the partition of Y. If yes, X determines Y holds. Prune. If X does not determine Y, any superset of X cannot determine Y either. So we stop exploring that branch. This is the downward closure property. Combine build larger candidate sets by joining smaller ones that pass the test, similar to the a priori algorithm for frequent item sets. Validate for every candidate X determines Y that survives. Scan the table to confirm that no two rows have the same X values but different Y values. The output is a set of FDS that likely reflect real constraints. In practice, noise and errors may produce spurious FDS, so analysts often set a support confidence threshold. For example, X determines Y in 99% of rows before accepting a rule. Functional dependencies enjoy several mathematical properties. Reflexivity, augmentation, transitivity are sound. They never produce false functional dependencies, and complete any true functional dependency can be derived using them. The proof of completeness uses induction on the size of the derivation tree. Armstrong's axioms are also independent. None can be omitted without losing the ability to derive some functional dependency. Counterexample: if we drop reflexivity, we cannot derive A determines A for a single attribute A. Closure operator: the mapping X maps to X plus is extensive. X is a subset of X plus, idempotent, X plus plus equals X plus, and monotonic. If X is a subset of Y, then X plus is a subset of Y plus. These are the three axioms of a closure operator in lattice theory. Counterexample to transitivity without proper premise. Suppose we have a determines B and C determines D. It is not true that a C determines BD, because the two functional dependencies are unrelated. Transitivity only works when the right side of the first matches the left side of the second. Armstrong's axioms form a sound and complete inference system, which can be proved by showing that any functional dependency that holds in all relation instances that satisfy the original set must be derivable from the axioms. The soundness direction is trivial. The completeness direction uses a canonical relation constructed from the functional dependency set. These formal properties assure us that reasoning with functional dependencies is mathematically solid, just like reasoning with equations in arithmetic.